Hello and welcome to the last of the Momentum series for Mr. Pinder's GCSE revision videos. Before I start, I just want to say thank you very much to all the people who've left positive comments on my other videos. I do apologise it's taken so long to upload. If I'm perfectly honest, I've been playing around with other programs, seeing how I can make this whole progress better. But anyway, let's continue and get on with part 5. So, the question is a very generic question, if I'm truly honest. You usually find this in a whole range of different contexts. You could have the context of an airbag or a seatbelt, crumple zones, cushioning systems, etc. There's a whole range of different contexts that this question can hold, but basically it falls into the idea of how this safety device stops people from being injured. Now, it follows the same physics, so the best way to kind of prepare yourself for this question is to have kind of a general or generic answer which can apply to any of them and just alter it slightly to match. Now, all of these questions start off based on the same formula. F equals delta P over delta T. Now, this is the equation we came across before. Force equals change in momentum over change in time. Now, we also need to remember that momentum equals mv. That's another equation we've come across. Now, if this is momentum equals mass times velocity, if we wanted change in momentum, well, as we know, mass in a collision or in most situations is a conserved quantity, so it's a constant. So the only thing that's changing in this case is the velocity. If we substitute that back into the original formula, we get F equals m delta V over delta T. Now, what has this got to do with anything you may be asking, and why do we have to rearrange in an explanation question? Well, believe it or not, this is actually one of your first marks using either of these formulas, because that's the beginning of your explanation. This is an example of mathematical modelling, that we are using a formula and then using logic within the formula to explain a situation by comparing different values and different changes in values and how they'd affect the final value, which is force in this case. So, first mark is for listing that formula. Now, this can be worth anywhere between 3 to 5 marks, so I'm just going to basically assume it's a 5 marks, and we'll go on from there. So, first one is mentioning that formula. The second one is for making a logical conclusion. In a collision, so let's say the collision is happening at this moment in time. So the car has literally just hit the wall and we're in the process of the force acting upon the person. Well, what can we change and what can't we change? Well, mass. We can't really change the mass of the person in mid-crash, not unless a particularly nasty accident happens and part of the person flies off. Also, we don't want that to happen. It would definitely reduce the force acting on the person, because if mass goes down, force goes down. But we're going to assume the person stays nice and whole and in one piece, so mass cannot be changed. What about the change in velocity? Now, you are correct in saying that the velocity itself is changing. You're going from the speed you were before to 0. But what about the change in velocity? Is it changing? I.e., is the difference between your initial and final velocity, can we alter that value? Well, again, the answer is no, not without bleeding kinetic energy and transferring it into another form instantly. That's probably not the best way to describe it. A better way maybe to describe would say that we're getting rid of the kinetic energy, which we can't really do. We can't just make the velocity of the car in retrospect change. So that in the middle of a crash, the change in velocity is another value we can't alter. The time taken for the momentum to change, though, is something we can. So that leads us to our second mark, that in mid-crash, m and delta v cannot change. And then your third mark, delta t can be increased. Now, the fourth part is the relation. What would increasing the time taken, as in the time taken for the momentum to change, do to the force? Well, if we think about it, if we increase a denominator, we decrease the value of the number itself. So the fourth mark is the relation that increasing delta T will decrease force. And then the fifth mark is just relating that back to the original problem, that a reduction in force would therefore reduce the injury. And that's really about it. Just don't panic and fall into the trap of saying, oh, if I use an airbag, it'll absorb the energy or it'll absorb the force. No, it won't. That isn't what happens. Force won't be absorbed, energy won't be absorbed. It's conservation of energy, so we are getting the same energy out. All we're doing is transferring it to other forms, sound and heat generally. I don't know if anyone's been in a car crash, but the airbag does get really hot. So remember this set answer method and use it whenever you recognise it as one of those questions, and hopefully you will score 4 marks. And that's it. That's the first series of videos. I'm taking requests. I've got a bit of additional time here and there. So please do feel free to send in requests. You can send them either as comments, and I'll read them eventually, or if you're a member of Notre Dame School, feel free to email me. I hope you enjoyed them. I hope they've been useful, and all the best in your exams. Thank you very much. Bye.